The sky vanished behind a towering wall of volcanic ash as Mount Etna spewed massive ash clouds high enough to choke flight paths and blot out the sun. Experts watched the plume surge beyond forecasts in real time, stunned.
Seeing new pictures this afternoon of Mount Etna erupting in the dead of winter. The Italian volcano surged to life again shortly before New Year's Eve. Amazing. And a river of lava is now making its way down the ice-covered slopes.
The first confirmation did not come from the ground. It came from orbit. Weather satellites began flagging a dense vertical plume rising from Mount Etna that expanded faster than automated tracking systems normally register. Within minutes, thermal imagery showed a column punching upwards through cloud layers and continuing higher, eventually reaching estimated heights of 12 to 14 miles, which is tall enough to brush the lower edge of the stratosphere. Live summit cameras that had been clear only moments earlier faded into gray static as ash density overwhelmed visibility. Nearby towns reported daylight dimming as if a storm front had rolled in, yet radar showed no rain systems anywhere nearby. Pilots flying regional routes relayed sudden haze walls forming along the horizon, forcing course adjustments before official advisories were even issued. The eruption was not dramatic because of lava fountains or glowing rivers. The defining moment was atmospheric domination. The volcano had seized the sky, turning airspace itself into the primary hazard within minutes.
It's a spectacular sight and it had tourists on the hop. Mount Etna erupting in dramatic fashion, the world's most active volcano putting on quite the show.
Volcanic ash is often mistaken for smoke, but the two are completely different substances. Smoke from fires is mostly carbon particles and gases that disperse and thin out as they travel. Ash, by contrast, is made of tiny fragments of rock and volcanic glass sharp enough to scratch metal surfaces. Under a microscope, these particles look more like shattered windows than soft soot. Because they are heavier and abrasive, they do not simply fade into the air. They hang, drift, and grind against anything they touch. This is why aircraft engines treat ash as a critical threat. When sucked inside turbines, the particles can melt, fuse to blades, and choke airflow within seconds. Visibility also collapses faster because ash reflects and scatters light rather than absorbing it. In motion, it behaves less like fog and more like airborne sand, reducing sightlines to near zero. The danger is flying through pulverized stone suspended thousands of meters above the ground.
Thanks, Fuego.
Initial altitude estimates were revised upward repeatedly as new satellite passes arrived. Early measurements placed the plume near 9 miles, already high enough to interfere with commercial jet corridors. Within the hour, updated models pushed that figure beyond 13 miles, rivaling the cruising height of long-haul aircraft. For comparison, many of Etna's routine ash emissions remain below 6 miles and disperse regionally. This event doubled those norms. The difference between tropospheric spread and stratospheric injection is not just technical. It determines how far ash can travel. In the lower atmosphere, wind and moisture break particles apart and bring them down relatively quickly. In the stratosphere, air is thinner and more stable, allowing ash to drift across entire countries before settling. Sensors indicated that a portion of the column briefly crossed that boundary, giving the plume reach far beyond Sicily itself. Height was not a visual spectacle alone. Altitude translated directly into distance, duration, and the scale of disruption that followed.
Go on, blow, man, blow.
Forecast models leading into the eruption suggested moderate ash output consistent with Etna's frequent activity cycles. Instead, real-time data showed vertical acceleration rates climbing far beyond predicted thresholds within the first minutes. Meteorological conditions played a decisive role. Wind shear at higher altitudes, which normally tilts and disperses ash columns, aligned in a way that funneled rising material upward rather than sideways. This created a chimney effect that amplified height instead of spreading density. Monitoring stations also recorded unusually rapid pressure release, meaning gas expansion inside the vent was stronger than simulations anticipated. Experts were not stunned because Etna erupted. It erupts often. The shock came from how efficiently the column defied expected atmospheric resistance. The eruption did not break historical records, but it outperformed short-term projections by a wide margin. The gap between prediction and reality forced rapid reassessment. In volcanic monitoring, exceeding norms is noteworthy. Exceeding forecasts in minutes is what truly unsettles specialists. Within minutes of the ash column breaching major flight corridors, aviation authorities shifted from caution to full red alert status. Volcanic ash removes both protections at once. Unlike storm clouds, ash plumes often appear thin or even invisible on cockpit radar, giving pilots little warning before contact. The real danger begins inside the engines. Microscopic glass particles melt under turbine heat, then re-solidify on internal blades, choking airflow and causing sudden power loss. Even brief exposure can sandblast windshields and pit metal surfaces, reducing structural reliability over time. Air traffic control centers began rerouting inbound and outbound flights across the Mediterranean, creating long arcs around the hazard zone instead of straight paths. Temporary no-fly sectors expanded hour by hour as plume models updated. Some regional airports paused operations entirely, not because the sky looked dark, but because altitude charts showed contamination where eyes could not. The risk was silent and mechanical. Ash did not need to be seen to be dangerous. At cruising height, one invisible cloud could disable an aircraft before pilots realized they had entered it. As the plume drifted inland, the threat shifted from airspace to rooftops and streets. Volcanic ash may look like soft powder, but its weight tells a different story. A layer only a few centimeters thick can add hundreds of pounds to a single building roof, especially when mixed with moisture. Older structures and flat surfaces face the highest strain, sometimes bending or collapsing under loads that resemble wet concrete rather than dust. Roads also transform quickly. Fine ash reduces tire traction, clogs drainage channels, and turns intersections into slippery gray film that behaves more like loose sand than dirt. Vehicles lose braking efficiency while visibility drops, increasing accident risk even during daylight hours. Power systems suffer in quieter ways. Ash particles conduct electricity when damp, allowing small discharges to jump across exposed components. Substations and transmission lines can short or overheat without flames or explosions, simply from contamination buildup. Water treatment plants and air conditioning systems also struggle as filters clog. The disruption does not require deep burial. Even thin coatings settle into every surface, creating friction, weight, and electrical instability that ripple through daily life far beyond the eruption site. Once ash rises high enough, its journey depends less on the volcano and more on the atmosphere above it. Different wind layers move in different directions, almost like invisible highways stacked on top of each other. A plume that appears to drift east at ground level may actually split apart higher up, sending portions north or south at the same time. Particle size plays the biggest role in how far ash travels. Larger fragments fall quickly, often landing within tens of miles. Medium grains can remain suspended for hours before settling. The finest particles, however, are light enough to stay aloft for days, carried by upper-level currents that circle entire regions. Moisture, temperature, and air pressure also affect how long those particles float before gravity finally wins. This is why ash from a single eruption can appear in distant countries while nearby towns receive only a light dusting. The volcano provides the launch, but the sky determines the route. The smallest pieces become long-distance travelers, spreading silently across borders long after the eruption column itself has faded from view. As ash began settling across nearby towns, the concern moved from dramatic visuals to everyday breathing. Volcanic ash is not poisonous gas, and it does not behave like smoke from a fire. The danger comes from its texture. Each particle is made of tiny fragments of rock and glass with sharp edges, more like powdered sand than soot. When inhaled, these particles can irritate the throat and nasal passages, triggering coughing, dryness, and short-term breathing discomfort, especially for people with asthma or existing lung conditions. Eyes are equally vulnerable. Fine ash drifting in the air can scratch the surface of the eye, causing redness, tearing, and a gritty sensation that feels like wind-blown sand. Public health advisories often focus on simple precautions rather than panic. Wearing basic masks, closing windows during heavy fall, and rinsing eyes with clean water usually reduce most irritation. The emphasis is on protection, not alarm. Unlike chemical pollution, ash does not spread invisibly throughout the bloodstream or linger as fumes. It settles, it accumulates, and it irritates through contact. The risk comes from abrasion, not toxicity. Understanding that distinction helps communities respond calmly while still taking practical steps to protect lungs, eyes, and indoor air quality. While ash drifted across the sky, scientists were not relying on ground reports alone. Modern eruptions are tracked from orbit in real time, turning satellites into constant observers above the cloud layer. Thermal imaging sensors detect heat signatures at the volcano's summit, revealing fresh bursts of material even when weather obscures direct view. Infrared instruments follow the ash plume itself, distinguishing volcanic particles from regular weather clouds by measuring how they absorb and reflect specific wavelengths of light. Radar systems add another layer by estimating cloud thickness and density, allowing experts to see not just where the plume is, but how concentrated it becomes at different altitudes. What stunned researchers during this event was the speed and scale of activation. Multiple instruments registered sharp spikes almost simultaneously, painting a wide and rapidly expanding footprint within minutes. Instead of gradual growth, the data showed a sudden atmospheric injection that spread faster than forecast models suggested. These tools do not simply confirm that ash exists, they map its movement, height, and intensity hour by hour. The surprise was not the eruption itself, but how quickly the monitoring screens filled with overlapping alerts from independent systems all at once.
Oh, look at that! Look how high those ballistics are.
The final realization was that flowing lava was never required for widespread impact. Many people picture eruptions as rivers of molten rock, yet ash alone can close highways and interrupt power systems across entire regions. The true reach of a volcano often depends less on how much lava pours out and more on how high its particles rise into the atmosphere. Once ash enters upper wind streams, geography matters less than air currents and particle size. A moderate eruption with a tall plume can disrupt more territory than a larger eruption that stays low. Cities hundreds of miles away may experience dimmed skies or thin coatings on cars without ever seeing glowing lava. What governs this behavior is physics, not spectacle. Wind direction, altitude layers, and grain weight decide where the effects travel and how long they last. In this case, Mount Etna did more than release material from its summit. It reached upward into the atmosphere and altered the space above daily life, influencing aviation routes, sunlight clarity, and air quality far beyond its slopes. The eruption changed the environment overhead, proving that a volcano's power is not limited to the ground beneath it. If this ash cloud darkened skies, grounded flights, and reached countries far away, what will happen if the next one rises even higher? Let us know your thoughts in the comments.